the root
squared, which is simply x squared plus 1, times
2x. 1/2.
Yes.
2x.
The square root of x squared plus 1 times
2x.
2x. Awesome. Yes, I will simplify. And yes, I have x at the top. Yes, I have in parentheses x squared plus 2 and the square root. So let's review this one more time. So if I have a function here, if this is a function, I have 1/1 plus the function squared, but then times the function prime, because this is not 1. If this piece prime is 1, I don't need it. But this piece prime is not 1. What is this function prime? 1/2 the square root of x squared plus 1 times the inner function prime, which is 2x. So this f prime must be here. And this is the f prime. And now I can condense it. After I simplify the two factors, only x is at the top. And what do I have here? It's x squared plus 2. What do I have here? Is the square root of x squared plus 1. I only request, yes, go ahead. Sorry.
Sir, could you please explain how you got the 1/1 plus x squared plus 1 again?
Yes, right here. So if this is the function, you have in the denominator 1 plus the function squared. But when I square this, I get x squared plus 1. Better?
Yeah, thank you.
Thank you. I only request these three. As you know me, I will test you on basic information. So I don't need the arc cotangent, arc cosecant, or what did I say? Arc secant, arc cotangent, arc cosecant, and arc secant. I don't need those three. I only need the basic ones because these are the ones that you will see again for sure over and over in Calc 2. So I would like you to remember, because if we need to look at all these basic derivatives, then making progress will be more difficult, right? So arcsine prime, arc cosine prime, very easy to remember. Same thing, with just cosine has a minus in front. And arctangent is totally different. Okay, so let's finish this up with any example. Oh, where is my book? So only arcsine, arctangent, and arc cotangent. Arc cosine, arcsine, arc cosine, and arctangent. That's all I need. If I want anything else, I'll have to give you the formula. I'm not expecting you to memorize anything but these three in the inverse trig functions. If you don't choose, I don't need this. Just the basic. Arcsine, arc cosine, arctangent. Anyone would like to choose, or I will? I will choose.
Can we try 78?
78. Yes, let's try 78. Okay. Y equals arctangent of the square root of 1 minus x over 1 plus x. Very good. So this is a mess, which is fine. This is a function. The square root is another function. The rational piece is another function. So I have arctangent, then I'm going to differentiate the square root, and then I'm going to differentiate the innermost function, which is the rational function. 1, 2, 3. Good. So y prime, I remember the formula for arctangent is 1/1 plus this squared, 1 minus x over 1 plus x, times, now this whole thing's prime. So arctangent again is 1 over 1 plus this squared. It's the square root. When I square it, it clears the square root. But now I have to differentiate this piece. And when I differentiate the square root, I have to have 1 over 2, the square root of whatever, times the innermost function prime, which I see it's a ratio. I know to differentiate a ratio, I have to have 1 plus x squared in the denominator. And now I have to use the rule that is the quotient rule. 1 over 2 prime. 1 prime times 2 minus 1 times 2 prime over 2 squared. The top prime, -1, times the denominator, minus the top. Luckily, the denominator prime is 1 because I would have had to write it on my desk. I always run out of room, as you know, there's no secret. Okay, it's messy. I have to try to clean it up a little bit. Let's stop for a second and see if we have questions. So let's do this again. Arctangent of whatever prime is 1 over whatever squared. 1 plus 1 over 1 plus whatever squared. Done. Now, I need to differentiate the square root, which I know how. 1 over 2, the square root, times the inner function prime. But the inner function prime is a ratio. I have to use the quotient rule. The denominator has to be squared. The numerator prime, -1, times the denominator, and then minus. The numerator, 1 minus x. Luckily, this prime is 1, because I would have had to multiply it here, but luckily is 1. So what I'm going to do is, I have to perform the operations here, which means I have to multiply this by 1 plus x, because its denominator is 1, and the least common denominator will be 1 plus x. Here, I'm going to flip this fraction. It will be 1/2 the square root of 1 plus x over 1 minus x. And here, I don't know what is going to happen. Something will go away, but I have to clean that up as well. Are we ready to continue, or do we need more explanation here? Okay, you will let me know. So then y prime, 1 over 1 plus x plus 1 minus x over 1 plus x. It can wait for a moment. This one is 1/2, but I have to flip this, the square root of 1 plus x over 1 minus x, times. Okay, then I have here a -1 minus x minus 1 plus x over 1 plus x squared. These two go away. Okay, so y prime, this goes to the top, 1 plus x. These two go away, so over 2 times 1 over 2 times the square root of 1 plus x over 1 minus x. -2 over 1 plus x squared. Interesting, very interesting, very interesting. One of these two will go away. The +2 here with the -2 here will go away. And finally, y prime. Negative in front from here. 1 over 2, 1 plus x, the square root of 1 plus x over 1 minus x. So I cleared one of these two factors. I cleared the 2, but I still have a 1/2 in front. I still have the negative. I still have a 1 plus x that is left over. Okay, I had 2 here and only 1 over there, and I copied the square root. Any questions? Any questions? Do you think we need to look at another? Do you think we need to look at another example? I'm going back for a second because I realized that I wrote 3.10, but it's the last section is 3.11, the hyperbolic functions. So please correct that. It's not 3.10, it's 3.11. Okay, so let's go back. Do we need to look at another? Is that a yes? Is that a no?
Can we do 68?
68. So in 68, we have g of x, arc cosine the square of x. Very good. Awesome. So g prime, so remember arc cosine prime is -1 over the square root of 1 minus this squared. Oh, nice. Times this prime, the inner function prime. What will that equal to?
One over square root f.
That's it. Done. There is nothing else we can do here. You can rearrange it if you want to as 2 the square root of x and then the square root of 1 minus x. Or leave it alone because I just didn't do anything really. Any questions? Okay, so I just would like to present 3 hyperbolic functions. So this is 3.11. There are 6 and they have 6 inverses. I'm not even going there. Hyperbolic functions. So when they looked at this function, which has no trigonometry in it, so if you want to graph something like this or something like this, these are no trig functions, right? But if you graph them, you will see that they look very similar. With this one looks something like this. It looks like a sine maybe. And this one kind of looks like a cosine. In a way, not really looking, but what happens is this is called hyperbolic. Some call it sinh. I don't like that, but it's up to you. It doesn't matter. I call it exactly what it is, hyperbolic sine. But where does this sine come from? I mean, this is no trig function. How come that we're using the notation sine, hyperbolic sine x of x, hyperbolic cosine of x. So what are we talking about sine and cosine here when these functions are exponential functions, some combinations of exponential functions? Well, it turns out, amazingly, that these functions, for example, they behave like trig functions when it comes to identities. For example, hyperbolic cosine squared x. We will not go into these properties. They're not required per se. So hyperbolic cosine squared minus hyperbolic sine squared, this will be 1. hyperbolic sine over hyperbolic cosine, this turns out to be hyperbolic tangent. And what is hyperbolic tangent? E to the x minus e to negative x over e to the x plus e to negative x. So I'm going to share my screen for a moment, and you can say, really, don't we have enough functions? Why do we need these? So I want to give you an example here, because I like the pictures in the book. I have never been to St. Louis, but the arch at the entrance to the town is a hyperbolic cosine function. I want to go back here. I want to see the graphs. I'm not going to ask anything about hyperbolic inverse functions. See, so when they built those, in the past, we used to have, as you probably know, telephone poles. So they needed to determine the length of this power line between the two poles. So it doesn't, based on weight, based on distance between the poles, and so on and so forth. And what they did, look, the best possible function going through these 2 points is a hyperbolic cosine function. Also, the water waves, they couldn't fit a polynomial function. They couldn't fit any other function. But they did fit a hyperbolic function, hyperbolic cosine. The architect who built the arch at the entrance to St. Louis used the hyperbolic cosine function to build this. So there are a lot of applications. As you see, hyperbolic cosine, this is very similar to sine squared plus cosine plus, right? Plus cosine squared equals 1. And all the other identities are very similar. So that's why they came up with this name, but they are not trig functions. They are combinations of exponential functions. Okay, so let's go back. Where is my arrow? Let's go back and choose, and then I'll stop. Oh, because I also have to mention something very interesting. So hyperbolic sine prime, as you would have expected, is hyperbolic cosine. And hyperbolic cosine prime is not minus, but also hyperbolic sine. And of course, hyperbolic tangent prime is hyperbolic secant squared. We're not going to look at the inverses. We're not going to look at the derivatives of inverses. Those are when you have a table of derivatives. There is no need to go that far. So let's choose an example or two, and then we'll stop. I would like you to have this so you can start working on the derivatives assessment, please. Okay, these are just identities to prove. We can look at limits, but I just wanted to differentiate. So find the derivative, simplify where possible. So these are the hyperbolic, sine, cosine, and tangent, and their derivatives. And let's just work on an example, and then we'll stop. They are not trig functions. They are combinations of exponential functions. And by the way, how do I evaluate this? I don't know if the calculator has hyperbolic sine, hyperbolic cosine. So if I want to evaluate, let's say, hyperbolic sine at 3, I will have to enter it like this: hyperbolic sine of 3. So I have e to the third power minus e to negative 3, and you know I love my parentheses, divided by 2. This is hyperbolic sine of 3.